Okay, good morning, everyone. So today I would like to share my recent work, which is about the quantum magnetic sensing inspired by Avian campus. So for this work, we collaborate with Zheng Yuanzhong in NTU. So, um, so for this migratory bird, it's a regular thing for them to move from one position to the other position, which is far away. So let's take a look at let's look at the right figure here, and we can find that actually they're tracking this eagle from Taiwan, and so this eagle actually they move every year. So they're from Taiwan to I think that's from Shandong and back to Guangdong. Then for the other years, they even moved to the Russia. So actually, this is a really long distance traveling. So how could this animal can really have the precise traveling on the Earth? So there is a model that proposed that the animal can actually sense the magnetic field from the Earth and use this as a cue and something like the GPS, the navigation system, can sense this external cue for them to find the correct track. So the model had been proposed is that, so actually for this bird, the retina of the bird has a radical pair, and this radical pair can really sense the magnetic field from the Earth. So um, another way that why there's a radical pair in the retina. So we can look at the figure here. We can find that at the bottom of the retina, you can actually there's a cone cell and rod cell. And for the rod cell, right between the membrane, there's the protein called krypton. And this krypton has a small component called flamin and tryptophan. And this flamin can actually stimulated by the blue light from the eyeball. And one electron had been excited, and then the electron hole propagate out and to the tryptophan here. And so here we can see that there are two unpaired electron located at this molecule, inside this molecule. So in this system, we can find that the radical pair is actually activated, induced by the blue light. So this radical pair can use for the sensing magnetic field. So with this model, the Hamiltonian that for the system description could be described by the Hamiltonian, which is composed of the flamin, tryptophan, and the interaction. So for the Hamiltonian of flamin and tryptophan, it actually composed of the Zeeman effect and Haber-Fine interaction. And for the state of electrons, for electron spins, so this electron spins is actually initiated by the blue light by the singlet state because of spin momentum conservation. The only singlet is eligible for initial state. And then within the time, the dynamic of the spin state is controlled, governed by this Hamiltonian. So the spin state has an interconvention to singular state. So they just can have this kind of transition from singular state to triple state back to singular and triple state. We need to note that when the radical pair is at the single state, there is the possibility to recombine them, which means that the electron back to the stable state, is a ground state, and this is called the recombination rate. And this recombination rate actually describes the lifetime of the radical pair. So this is could be analog to T1, T2 times at this sense. Then for the spin state, the singlet state or triplet state can actually produce downstream chemical that can regulate the animal's behavior. For example, that now we look at the single state yield. This single state yield will change the protein formation, which will in turn eventually regulate the protein on the neuron that result in control of action potential. This will affect the decision making of the animals. So here we can simplify this system as a one proton and two electron system. Right. So for this description, it had been the expression of the singular yield had been derived by Peter Hall in 2009. That in the also in 1998 in molecular physics. So for this system, the system is described by the Hamiltonian composed of one nucleus and two electrons, and only one electron is connected with are affected by the Hepburn interaction from the nucleus. So the Hamiltonian is very simple. And the omega here, omega is the magnetic field. So with this Hamiltonian, the state of the system could be evolved and could be represented like this with the initial state sigma 0, and with the Hamiltonian defined by here, and then we can, because the initial state is a singlet state, so eventually we have the density matrix that changes with time can be expressed as this formula. And with this time-dependent density matrix, we can find the portion of singlet state from this density matrix by writing in this expression. And then we can eventually have the formula, which is that it depends on omega mn, where the omega mn represent the energy gap between any two states. I forgot to mention that here we only look at the state of the electron could be singlet and triplet. So singlet is because of the magnetic moment is equal to 0, and for triplet state they are equal to 1. So with this expression, we can bring some parameter into the system, into this expression, and find the time dependence of this singular yield. Here, although we are plotting, they are plotting on triplet, but actually they are 1 minus rho t is equal to rho s. So never mind, they are the same. So we can find that the time dependence could be plotted in this way, and this frequency is actually determined by this omega mn. Then if there's no recombination rate, if there's no recombination, this frequency is purely if there is no magnetic field, this frequency is just purely determined by this Hepburn interaction. However, if we are considering this magnetic field, and then this magnetic field will eventually regulate this pattern by a small envelope. The slow envelope frequency actually represents the information of magnetic field. So this gives us think of that we can identify the strength of magnetic field by looking at the information which is encoded into this system. So far, any question?
I have some question about the notation.
Yeah.
So in the previous slide, can you elaborate more about the rho S and rho T? How it is, are they the singlet and triple stay?
Yes. So here in this slide, I'm going to talk about more detail about that one.
And can you explain what's the capital P? Are they dipole or what?
So P, are you talking about this one?
Yeah.
Okay.
In previous slide, you also have P, but it PS in the second line, PS corresponding to sigma 0, sigma T.
Yeah, because the initial state is in singlet state.
So P stands for what? For dipole or for what?
P. Sorry. So let's look at this line. Okay. This is the same P.
Okay.
Okay. So then, do you have any other question for previous slide? Otherwise, I can start from this slide to answer your question.
Okay. Maybe can you say what's the recombination you are talking about?
Okay. Recombination is like here, because actually at the beginning, when you shine a blue light, the electron was excited and the electron hole was propagated throughout. Then here there is appear the unpaired electron here. So that's the way the radical pair had been formed. But however, when the time is long enough, then there's a possibility that everything will go back. So the lifetime of this radical pair determined by when they recombine. So the recombination rate is the inverse of the lifetime of the radical pair.
So I'm asking in the Hamiltonian, you are showing how to determine the recombination.
Right. So recombination rate, I didn't show that here, but somehow we can find from here. Here, the recombination rate is inserted from this term. So maybe we can start from this page, this slide, then we'll explain more about that. Okay. So for the work from Peter Hoare, you propose a very simple model, but even this model is simple, but they actually catch the main idea or fundamental property of the real system. So that's why it's worth for us to look at this simplified model. So okay, let's look at the Hamiltonian, and this Hamiltonian is consists of the. Sorry, here I've changed the notation, and I changed the notation field to theta, and then we only look at this magnetic field only in z direction, and only spin A has hyperfine interaction from nuclear spin. Okay. So given initial state, which is sigma 0 that I mentioned before, but here, okay, then this system will evolve with time, and which is governed by this Hamiltonian. So something that singular yield is the signal. It's very important signal for regulating the signal cascade and could control the animal's behavior. So there's fraction of single yield could be written in this way, which is the trace of rho S times sigma t, which is that you use the density matrix project to the singular state to see what is the portion of the singular state at some time. So here the PS is single state, but here our system is composed of one nucleus and two electrons. So the electron state could be expressed in this way: this singlet state, and tensor product with the state of nucleus. And here the single state is represented as 0, 1, minus 1, 0. Here the ms is equal to 0, which is generated by nature, right? Does that make sense? Okay, so right now we are at the time to look at the total singular yield, and this total singular yield can be represented by like this. And so here we consider the time, the recombination rate, which is the inverse of the radical pair lifetime. And then we integrate this to the exponential decay. This is the assumption on the Poisson process, which is that we look at this recombination has the exponential decay. Then by integrating this, we can eventually find the system represent like this. So here we can find that this total singular yield is actually depend on the initial state and your projection, and also the omega mm, and where omega mm is the energy gap between state, between M mode and M mode. So here, basically, this is just the energy gap, and this is the initial state, and this is a projection to the single state. So, Minjian, is that answer your question?
So your recombination rate is actually the K.
Right. Recombination rate is the K.
And
yeah.
This is the phi s is the actual formula, or is the formula you are using to fit the evolution. What's the case? I mean, this.
So let's take this figure, and this is the phi s. This figure is from the paper from Peter Hall, and in this figure they look at the effect of recombination rate. So when the recombination rate is fixed to 0.005, and you can find that this total single yield is changed with the theta, which means that the single yield is actually response to the different magnetic field. And when they increase this recombination rate, they found that this response is getting smaller and smaller. And eventually, when you have strong recombinations, high recombination rate, the curve is flat, which means that the singular yield is almost a constant to every magnetic field strength. So in this article, they find the important conclusion is that the recombination rate should be small enough for the system to respond or to sense the magnetic field. Yeah. So they also provide an analytical expression for these things, and so they draw this curve based on this expression.
So in real application, you actually don't know K, so you are trying to fit the formula to your system, right?
They are not really fitting, but actually they perform their group. They're a very huge group. They have a lot of collaboration. They actually do some experiment to identify what a K should be, but it's in different system. But here we only look at the most trivial, like I think the representative one, to show people how this thing could affect the system.
I see. Okay. Sorry. One more question. I want to make sure your assumption on the nuclear spin.
Yeah.
You are using the identity.
Yeah.
So you are assuming they are in the totally mixed state, meaning that you don't assume any information about the nuclear spin.
No. Right. Yeah.
So
Right.
no means what?
No, I don't have. I just it's not me. From the original simplified model, they just assume that the spin could be either up or down. That's all. There is no interference term here.
Okay. Okay.
Mm.
Okay. Thank you.
Yeah. So for my work, I start with this simplified Hamiltonian. I will look at the different effect to the singlet yield. So here I'm going to look at the magnetic field, effect from initial conditions, and the recombination rate and the coupling strength. Because at the original work, people only discuss about the single radical pair. But however, in nature, the thing is that the radical pair could not never be isolated. They are always have a lot of this kind of protein. They are located nearby each other, so coupling strength could be play an important role for the system. So here I'm going to look at the effect of these four effects to see how this can change the singlet yield. So this is the effect of initial state. Here I consider classical initial state and a non-classical initial state. While the non-classical initial state is described by first the singlet superposition initial state. This is the assumption from the Peter Hall's original work. And this is also the expression we have seen before. Then here we have look at plus superposition initial state. So here, what do we mean by classical and non-classical is that for the classical state, there's a definite state. Like when you apply this, you can only measure O1. So the only thing you can only measure O1. You use O1. Sorry, I shouldn't say that. That's a definite state. You cannot You cannot get another state by projecting. Sorry, I should rephrase my work, but this tell you this is really a definite state. You cannot get the other state by applying this state, by applying the projection to this state. I think that's what I should say here. And then with this sigma, with this the classical initial state, the total single yield should be expressed in this way. For the plus superposition here, I just I consider all four possible spin state to the system. And so we write down the analytical expression for these three initial conditions, and we draw the response curve. This curve is the single yield change with the magnetic field. And from here, we can see that for the classical one, we can find that under the same parameter, the classical case tell you that the singlet yield doesn't change with the magnetic field, while the singlet superposition and plus superposition that really affected by the magnetic field at this low weak field range. So this tells you that probably some advantage for this non-classical state can give you for the sensing. The next step, we look at the effect of recombination rate. So from the figure, we can see that when we change the recombination rate, we can find that we can see here, like when we have a small recombination rate, the curve is at the below, and when we have strong recombination, the curve is the upper one. And we find that in classical state, this curve doesn't change with the magnetic field so much. However, when we look at this non-classical state, we can find that this actually give you so when you have a low recombination rate, actually we do have a very sensitive region here. But when we increase the recombination rate, and this the single yield doesn't change with the magnetic field. This result is also discovered by Peter Hall. However, here we found that when we apply the initial plus the superposition state to the system, then we find that the result is similar to the singlet superposition initial state. We find that when the recombination rate is very low, which means recombination, which is the radical pair lifetime is very long, then your response is very strong, but that only restricted at the weak field region, which means that even though you have strong response to the external field, but this only the working region is only at the weak field. Yeah. Any question here? Okay. So let's further define the field sensitivity. So here I need to write down this sensitivity in this way because this definition for the sensitivity is not intuitive for most of the people. So this sensitivity is defined by the minimum sensitive magnetic field, and this is equal to the inverse of this response. There's a partial phi partial theta. So when this is small, which means you are sensitive, you can sense the small field. So as it is small, which means the system is more sensitive. Then with this definition, we can look at the system. We can look at the curve. This curve is obtained from the previous analytical expression on the weak field approximation. And we find that in weak field approximation, which means that we just look at the field is very small. And then we find that when we change the recombination rate, the sensitivity doesn't change. This is for the classical case, but for non-classical case, we can find that this finding is consistent with the previous slide, which says that when the recombination rate is very low, then you are sensitive. You can sense the weaker magnetic field. But when we look at these two non-local initial state, which is singlet state and a superposition state, singlet state and plus superposition state, we found they are almost identical. To be honest, I cannot identify which one is better. So to identify which one is better, it's trivial to plot them together, and we can find that at the low recombination rate, there's a crossover between the singlet superposition and the plus superposition, and this position could be identified by putting them into a ratio and find the position. Find the critical K that give them when they equal to 1. So therefore, we can find that K star could be written in this way. So for this, so then we can tell that in this system, if your recombination rate is smaller than K star, then system should be probably have better sensitivity when the initial state is singlet state. Otherwise, plus superposition state will be better. So this physical realization for this result is that why for the relation for why the non-classical initial state will be better than the classical state is because of this there's an interference term, because the non-classical initial state give you a bigger space that allow the single yield can have large more single yield. Okay, so then after this isolated radical pair system, then we look at the coupled radical pair system. For the coupled radical pair system, and the system is described in this figure. So here I only consider two identical radical pair, and there's a connection between one of the spin. Here in this figure I consider the coupling is established between SB1 and SB2. The 2 means the second radical pair, the 1 means the first radical pair, and SA means the electron spin that can have a hydrophile interaction, and B is the electron without hydrophile interaction from the nucleus. So and G is the coupling strength. Then by looking at the system, and the Hamiltonian could be represented in this way. There's a summation of hydrophile interaction, while the theta is the external field, and there's a coupling between SB1 and SB2. So because the structure of the radical pair is not symmetry, so we may ask what. So there is 4 different ways for people can have the connection, because you can also choose SBB, SBBB, or ABBA. So we have 4 configuration for this connection, but however, because the SG for this one and this one, G2 and G3, they are the same. So there actually only 3 configurations we need to consider to see what is this coupling to affect the singular yield. So this is the response pattern of first radical pair and second radical pair under the G4 coupling, which you only consider the coupling between SB and SB1 and SB2. And we found that when we look at, because this the configuration is a symmetry, so the response pattern for pair 1 and radial pair 2 are identical. So we only need to take a look at the one of the figure, and we can see that there's a strong response, which from the origin and then split to the stronger magnetic field. So if we look at the G equal to 0, then system will be reduced to an isolated radical pair. And at this moment, this response is identical to a isolated, sorry. It's identical to a single radical pair. However, when we increase the coupling strength, we can see that the strong response is moved forward to the stronger magnetic field. So this actually interesting, because at the beginning for a single radical pair, the sensitive region is restricted at the weak coupling strength. Is restricted at the weak magnetic field. However, from this observation, we found that when we introduce the coupling between a radical pair, the sensitive region could be changed. And actually, this coupling strength could be adjusted by change the distance between 2 radical pair. Yeah. So if we look at detail by look at the sensitivity of the system, and we find that this good sensitive when coupling strength is 0, there's no coupling. When there's no coupling, the best sensitive region will be at the weak field. However, if you increase the coupling to 0.3, then you can find that the working region, the best working region will be located around the 0.2 to 0.3. And this means that the increased coupling will allow you to change your working region. Moreover, you can find that this sensitivity is almost the same, which means that allow you to change the working region while the sensitivity remain almost the same. So we may ask why this sensitivity region or this peak, this single yield peak, how this can be formed. So because the system is simple, so we can look at the Hamiltonian and then regard the coupling term as a perturbation term. So in this point of view, we have the eigenvector, which is composed of either radical pair 1 or radical pair 2, and then with the eigenvalues from the original system, and with the correction with the corrected term, which comes from this perturbation. And because the eigenvalue is modified, therefore the energy gap is modified. So eventually we are looking at the how this component could affect the singular yield, the total single yield, which represent in this way. So for here, we can from this expression, we can see that if in order to have a peak, either you need to have large PSMM or weak omega mm, which means if omega m equal to 0, which means that degeneracy happen. But so this is only about the eigenvector. Sorry, I read in wrong. This is eigenvector. This is eigenvalue. Sorry. So in order to have a peak, so this PSMM should have a bigger, and the degeneration should happen here. But actually, because of this is first order approximation, the eigenvector won't be changed when the perturbation changes. So when we increase the G, which means the coupling strength increase, we got the peak change. For sure, this should be that the effect comes from the energy gap between each mode. So yeah, this is what I told you that. So here we know that the PSMM doesn't change because this is only about the eigenvector, which is doesn't change with the perturbation term, and we want the omega m to be degeneracy and at some specific coupling, which I call G peak. And then I just told in short that we found that G peak could be right in this way. Then later on, I'm going to use this expression to tell you how to use this to identify the magnetic field. And this is more detail about how I get the G peak. So first of all, I just consider the coupling is between SB1 and SB2. And then I look at the mode which has large PMM. And I found that energy gap could only in this 8 mode, 8 energy gap. So within this energy gap, I should look at the degeneracy. So which means I need to ask omega, this energy gap becomes 0. And at this moment, I can find the G. But here, G, I need to be positive. So because of this condition, I figured out only this 2 is eligible for G peak. However, remember that our analytic expression for the coupling, and that's a perturbation. So only weak coupling is eligible for the system. So only this term is eligible for us. So because you see that is plus minus, so we have 2 coupling. and I define that for G1 and G2. For G1 and G2 is look in this way, and then our aim is to find the theta, which is magnetic field. So by add them together, and I can the magnetic field can eventually be deduced to 2 times G1 plus G2. This could be illustrated by this figure here, and we can see that when the theta is equal to 0.3, and we can tune the coupling strength between the two radical pair. And then we can find that at some specific coupling here and here, we find that there's the G1 and G2. And here we find that G1 is 0.064 and G2 is 0.086. Then I follow this formula. I insert this value inside, and then eventually I got the theta equal to 0.3. And this is the way that I can use the system to obtain the magnetic field. Is there any question here?
Sorry, can you remind me what's the omega?
Omega. This omega?
No, capital omega.
Sorry. Oh, this omega is defined by long time ago. So the omega is defined by the year.
So it's a parameter about theta. Okay.
Yeah, yeah.
And then G1 and G2 refer to coupling separately to first electron, first pair and second pair.
G1 and G2. Oh, sorry.
Yeah.
I defined that G1 and G2 is that peak, first peak and second peak. Okay, here we only, so by choosing the eligible coupling here, right? We only have this one is what we want. But here we have a plus and minus. So I write down plus here, minus here, and define the first one is G1 and the second one is G2.
Okay.
Yeah, and with this expression, I can extract this theta by adding them together, because in this moment, omega is cancelled, right? So the only thing we left now is that theta is equal to 2 times G1 plus G2.
Yeah, I see. Yeah, so
right?
The first peak and second peak you are trying to say.
Yeah, G1, yeah, what's first and second peak here. So for example, I just say illustrated in this figure. For here, this is G1 and this is G2.
Mm-hmm.
Okay, because this is position for us to find the position for finding the peak, right? This is actually the position that degeneracy happened.
Yeah, I understand.
Okay, right. So once we get this to pick, we can get this information, and then by utilizing this information, then we can obtain the magnetic field, right?
Okay. Another question. What's the eigenvector m or n? You are referring to the eigenvector of separate single case, or are they just bases?
The eigenvector of the Hamiltonian.
I mean, separately, the notation mi and mj. What's the?
Yeah, separately, because they are additive, but they are different system, right? Because it's for one and for one is for two, so I separate them.
Okay. So they are already referred to eigenvector separately. Okay. Okay. I see.
Yeah. So let's continue that. So if we look at the different coupling, And here we can see that we compare the G4, which is so that in the previous case we only consider G4, but what if we consider G3, which is the connections between SB and SB1 and SA2? What happened to the system? And we found that the system, the radical pair, see that the radical pair 1 is actually connect to different spin. For the G4, they connect to SB2, which is the free electron without hyperfine interaction. And here in G3, the SB1 actually connect to the electron with hyperfine interaction with nucleus. So with this difference, we can find that the response pattern is actually very, very different. The position is the same, but the strength is it became weakened. So this means that by coupling two different parts of radical pair, the response could be different. I would like to know what happened by connect to this spin A2. And so similar trick. I apply the first order approximation, and because of this coupling only contribute to the perturbation term, so the eigenvector will be the same. And because this only contributes to the perturbation, so the eigenvalue will be corrected by the connection between radical pair. So which means that the energy gap will be different. So according to this numerical checking, then I find that for the system with G3 connection, we find that the term, the degeneracy component, or is the number of degeneracy component is smaller, is less than the one with G4 coupling. Yeah. So which means that because the coupling to which electron is very important, because this coupling will affect the degeneracy, how degeneracy will look like, and this will eventually will have you different response, something like sensitivity or response region or working region, something like that. Okay, so far that's a two-coupled radical pair system. So what if a multi-coupled system? So for the multi-coupled system, I'm looking at the effect of system size and the effect of connectivity. So here we look at, so let's look at the result here. Start from here. I introduce the radical pair chain and they couple in this way, which is a B1A2, B2A3. That is the chain structure. And from here, we can see that for the radical pair 1, the response pattern is like here. That is that radical pair 2, the response pattern become more complicated, and the radical pair 3 become like this. So because this connection is B1A2, B2A3. So so here I just refer to the two-couple system, and we can find that there's a B1A2 system, and you can see that the response pattern for two-couple radical pair system is actually the same is identical to the radical pair 1 in a three-couple radical pair system. And also this radical pair number 3 is identical to the radical pair number 2 in two-couple radical system. So so here what I want to say is that response pattern is only associated with the coupled spin, because this is a local coupling and we apply the local measurement. Therefore, the effect should be only restricted in a local. Then I enlarge the system into 4 coupled radical pair system, and same result is the result is the same. But I found that here we found that no matter how long the chain you are giving to the system, the response pattern is identical. For example, when we look at the edge and the edge, they are the same. And when we look at the node at the middle, and they are also the same. Yeah, so here we have a conclusion that the system size doesn't matter. The thing that only matter is that which spin you are connected. Okay. So then let's look at the connectivity. So and here when we look at the connectivity, I only consider the G4 coupling, which is look at the connection is established between SB1 and SB2. So for here, we can see that if we look at the three coupled radical pair and connect in this way, and we found the same result as before is that the H1 were identical with the H1 were identical to the G2 coupling system. However, in the middle is very different because here we can see that you have two neighbors and they're coupling in the same position. So you can actually find the response, the line is actually happen at a weak coupling, which means that the effect from two neighbors actually contribute to the same size. So with a smaller coupling, then you can respond to the higher magnetic field. So let's look at the neighbor. The size of neighbor is 3. Here is 2. It is 3. And here we, for the peripheral edge, peripheral node, you can see that the peripheral node show the same behavior as before. However, when you look at the center, the node at the center, which is node number 2, and you see the node number 2, that's very tricky. It's very interesting because you can see that the pattern here is identical to the pattern here. You can see here, but this new pattern that from the edge appear to the central node, which may give us that because of this coupling, the structure of Hamiltonian matrix could be very different. Some structural change allow you to have this kind of behavior. Yeah, so anyway, no matter what, increase of the coupling will make the thing complicated, and we need to see what happened. We need to have a further investment for this system. So far, any questions? No. So here we are summary. So in this work, we perform a magnetic sensing by showing the pattern of a simple radical pair, which is a 1 proton, 2 electron system. And we also look at the effect of different initial condition. We introduce a non-classical initial condition and to see that the contact advantage had been observed from this non-classical initial condition, and this could be result from the larger Hilbert space. And then coupled radical pair system is this the behavior of a coupled radical pair is also being investigated. And this shows that collective sensing enable more general and flexible sensing mechanism, because at the beginning we know that for single radical pair, the only weak magnetic field could be the only response to the weak magnetic field. However, for coupled radical pair, we found that the sensitive region could be changed by changing the coupling strength, which will be in terms of changing the distance between radical pair. Then this mechanism is mechanism is explained by the first order approximation, and this tells you that the formation of the peak, and which also can predict where should it be the peak. And use this mechanism, we can think of a new method for people to understand what and where the magnetic field can be. And this magnetic field could be existed in different range, not only restricted to the weak field. And then other configuration like effect of different system size and the effect of connectivity is rather is also considered in our system. You find that the system size and the system size is not really important. The most important thing is that which spin you are connected. That's all my talk. Thank you. Any questions?
Any question from the audience?
I want to ask, in your case, you are trying to see the larger sensitive region, which means the change of EO larger. You are trying to find this regime, and do you put any numerical value estimate, like the compared to the magnetic field in the Earth?
Yeah, so no, because because this is a simplified system, so the real magnetic field from the Earth is about 50 microtesla. So here I didn't really consider hyperfine interaction, which is actually a tensor. So I cannot make some comparison because this is a simplified model. You know what I mean?
Yeah. So yeah, you are trying to see the behavior, but for the
I can only I can only compare quantitatively instead of qualitatively.
Okay.
Yeah.
And one more question. You only consider the change of the magnetic strength in a specific direction, like Z direction. You do not.
Right.
Okay, I see.
Right.
Okay.
You may ask what if other direction. Here I didn't consider that. But in other way, you can think that you can always rotate the radical pair.
I see.
Right. Yeah.
Okay. Thank you.
Any other questions?
Can I just clarify something?
Sure.
Can you go to the slide where you define the sensitivity as?
Yes. 1 second. Yeah.
Maybe the first one, the one with the before the coupling. Here, yes. I just wanted to check. So for the sensitivity, I guess if S is larger, then it's more sensitive.
No, here the S is small, be better. This is very counterintuitive for most of physics because here the field sensitivity was defined as a minimal detectable magnetic field.
Okay, I see.
Yeah,
I see.
so
Of course, you want to be able to detect a smaller field.
Right.
Okay.
And this actually this is the foundation. I have a kind of small argue with my former supervisor because he told me that is totally not intuitive to think of these things.
Yeah, I guess like maybe something like if you take 1/S, maybe it's more intuitive.
Right.
Something like that. Okay.
Right.
Yeah. That's why, because I was looking at the smaller plot on the right, bottom right, and then I was just wondering like, why is the singlet below the plus? And then I guess you wanted to claim that actually the singlet is more sensitive. Okay,
right.
but that's actually what you want, right? Because it's the
Yeah.
smaller. Okay.
Yeah. Thank you.
Okay, thanks.
Any other questions? or comment?
Sorry, what's the delta T here?
Delta T, oh, that's a sensitive time because for the system to sense the magnetic field, actually it's not really pound, just a sense at the moment. It's sometimes integration time.
So
It's
So-
more time duration.
so actually in the real application, you need to wait some time and integrate the
Yeah. Like you want to collect the photon, you need to have some time.
But in your formula, you are integrating over the matrix instead of some value, right?
In matrix.
I mean the density matrix. Because in
Oh,
the slide, yeah.
Yeah. But here we are looking at actually phi at big phi as here is already a value.
Okay.
And we integrate within a duration.
So phi s is also coming from some integration, right?
Right. Here we have a definition at the beginning.
Okay.
Here, actually, we only look at this by the time is restricted by the lifetime of a radical pair.
Yeah. So that's my question.
Mm.
Rho s is actually a matrix. So
I'm sorry.
phi s.
No. That okay. Professor Shi had told me that before, but here the definition is like this. There's actually have different because sigma t show the density matrix and rho is the fraction to find the
what?
state. Huh?
So rho s is
Fraction to find the single state from density matrix rho t. Sigma t, sorry.
Oh, okay. So it's already a number, a fraction less than 1. Okay.
Yeah.
Okay.
Mm-hmm.
Maybe one comment.
Mm-hmm.
In your class superposition, do
Yeah.
you think if you put different phase in different terms, that would be helpful, or do you want to try that, or you don't think necessary?
And you only consider coherence there. Different phase.
Like they are plus minus or however combination.
I don't think that would be changed so much.
Okay.
Yeah.
Okay, thank you.
Okay.
I'm done.
Okay, thank you. Any question, comments? No?
Okay. Any questions? Okay, if there is no further question, I thanks Wei-Yin for today's talk.
Thank you.
Thank you.
我走喽，下午2点见。
下午2点。